Yes. So following the book Stein and Shakarchi, okay, this is the book that I am roughly following. Okay. So Stein, Shakarchi, he has, I think, other books also on analysis, but we are obviously following complex analysis. Okay. But this is obviously not a course in hardcore complex analysis. This is just complex differentiation. We have proved some very basic results, but today's class does not need the previous classes as such. Okay. So we are at a place where we need to study special subsets. Okay. Special subsets of R2. Okay. Where surprisingly, where integration, we will need a lot of this, where integration can be done. Okay, and it has a certain other good features. Okay, so what is that special subset that we are trying to understand? Okay. I'll mention that, but before that, let me say that we will first study such subsets on R itself. Okay, we will try to understand them on R. Okay. Now see, when we are looking at the real line, yeah, and we are trying to do analysis on it, what are we trying to do? On some level, let's say there is some process running, you know, there is some particle that is moving and we are tracing it, and we are using the real line in one way to track the time, maybe as a time parameter, yeah, and maybe we are using the other, you know, to plot the speed or something like that. Okay, so that's why to do these things we usually use intervals. Yeah, intervals are special subsets. We are not interested exactly in this, but we will see that it turns out to be only this. But in R2 it's more interesting. But intervals, at least so this is something that we can all appreciate, right? Intervals are special subsets. These are number one. These are special subsets in R. What are some other kinds of special subsets? Yeah, and these are called, so let's see. So if you have a subset of R, okay, if you have, let's say, S, which is a subset of R, okay, and you are trying to study some process which for which S is serving as the domain, as something that is parameterizing time, something like that. And sometimes what you might want is, for any point in S, for any point in S, we can move a little. We can move a little. I'll formalize this, of course, but move a little and still be in S. Sometimes we are very much interested about these kind of subsets. So if you have done, obviously you have done continuity, basic differentiability, you will see that you need, for the definitions to make sense, obviously we make a different definition for endpoints, but usually in the end, the continuity at endpoints is a very different matter usually, since differentiability more so. But usually, how does the definition go? For any point, for any output, for any epsilon, we need a neighborhood delta around it, right? So for this, you see an honest neighborhood around the point must exist, which is basically what I'm trying to say more loosely as should be able to move and still be in S. Yeah, so these are other kinds of subsets which are interesting. Okay, these are some other types of subsets apart from just intervals. Intervals could include open intervals, closed intervals, half open, so on, right? But apart from all that, these are other kinds of subsets which, 1 second, so the fan is just 1 minute. Yeah. So what I was saying is these other kinds of subsets which we can be interested in, where we can move a little bit. Okay. So let me now define this. Can anybody try to define this kind of subset? If someone knows or someone can define it from or extrapolate from what we have been saying so far, can you define such subsets as this property and this property? How to define this? Really coming up with nice definitions is a very important skill, art, whatever. How to define S? I mean, S, which has this kind of feature. Where whenever you are inside S, you can move a little bit. Yeah. So this is basically saying that for all X in S, yeah, there exists some delta X such that this entire neighborhood, right? This entire neighborhood is inside S. Some of you may recognize this if you have done it, if you have seen that. These are also called open subsets. Yeah, the term that is used here is open subsets, but really it's not about the name. Yeah, I think it is more important to understand what is the essence of such subsets. Because then a lot of theorems where they will state a hypothesis, then that hypothesis will not look surprising, or you don't have to remember it. You would know that, yeah, this should be like that. You know, it will move natural. So this is what we are trying to capture. When you are inside S, you should be able to move a little bit. Obviously, open sets can be defined in many other ways. Okay, obviously equivalent ways. So formally the definition is S is an open set if for any X inside S, you have a neighborhood which is still inside S. Okay. Let's not go into different types of definition, because that is not the goal of the class. Okay, we're not trying to do topology. I'm just trying to do what is there in stain structure. This part will be there in the exercises. Okay, they move this as the exercises and then they use it in the next chapters. And obviously, someone has done a course in topology properly or something metric space is proper, then maybe this will not be very useful, but you can still listen to the perspectives I'm trying to present. Okay. But yeah, so these are special types of subsets. Okay. Now, the type of subset that we are interested in is not these two, though there's a certain reason why I have introduced those two. You will see when the time comes. So the third is what we are interested in is, I'll just say the name because the name is so nice. Open subsets name is also a nice name. It can be motivated why this is called open subset, but I'm not trying to give a lecture on open subsets today. So let's come to the main thing. Yes. There's a difference. So can anybody give an example of an open subset which is not an open interval? Or maybe you can think of one. Open subset but there is not a lot of difference in some sense, but well, it depends, but there is a difference. Open subset which is not. Absolutely. Yeah, the other way around is not true, as you can understand. Yeah, so this example, yeah. So obviously in general, you can have unions of open intervals. Yeah. So basically this also can be given as a definition, open subset, subset that is a union. Yeah. A union of open intervals. For every point you can find an open interval. I will assume that this is intuitively clear to everyone. If not, please ask. Okay. But still try to write a proof that these are all same. Yeah, this definition of open subset and a subset that is a union of open intervals, these two are the same things. In fact, much more can be said, but again, that is not that is specific to R, which we're not interested in too much. So, okay. So let me now remove some of the thing and move to the actual thing that I'm interested in. Yeah. So a lot of times when we are, openness is not enough. Okay. Openness is not enough. We are interested in subsets where you can continuously do something. Yeah. You can move around in a path in that subset, path that does not break. It doesn't have any holes. You can partition it cleanly. A lot of things of that nature. Okay. And it's important for many other also. Okay. Those subsets that we are interested in are called connected. Eventually, we'll be interested in something called simply connected, but that's a little more complicated to do. So we will not do it right now. Okay. But connected. Okay. We are interested in connected subsets. Now, how to define this? Okay. So again, the idea of a connected subset, yeah, is the idea, as I've said, the idea is that it is means you cannot break it up into two pieces. Yeah. Cannot break up into two pieces. Yeah. Now, obviously, anything you can break up into two pieces, right? But here we mean that two pieces which are kind of different from each other, not just on a set theoretic level, but also on the level of also geometrically. Okay, meaning that I will give a definition, but I'm just trying to explore the intuition. What do you mean by two pieces? For example, if I take yeah, let's try this. If I take this interval, right? Okay, some 2,5 closed interval. That closed or open doesn't matter. I take this interval, right? Now you can say that, well, why not take, it's a 3. Why not whatever, yeah? It's a little side. Why not take this? And this is a breakup. This is broken up into two pieces. But this is not, geometrically, this is not breaking up something into two pieces. Set theoretically, definitely is, yeah, into two pieces, but into two disjoint pieces, obviously. Set theoretically, yes. And I'm just saying these things because these things later on, when you do exercise it in connectivity, or even later on, more generally, something called irreducibility, and so on. So just for to understand this, these two are definitely two pieces set theoretically, no doubt. But analytically, limit-wise, they are not two pieces. Why? Because if you are at 3, which is in this piece, right? Okay. Then the 3 is not actually inside 3,5. Yeah. The 3 is not inside, the 3 is in 3,5. Yeah. But the 3 is not inside 3,5, right? Because if you make any neighborhood around 3,5, it intersects with 2,3. Yeah. Said in other words, 3 is the limit of 2,3, which I think you can really recognize. Yeah. So we don't want to break it up like this, such that so that there is a point here, which is the limit of a point here. We want to avoid such situations. Okay. We want to avoid such situations. Okay. Any point here should be truly in that, I mean that you should be able to move inside it. You should be able to make a neighborhood, make a zone which is completely, which it owns, which is inside its subset. Okay. So that is really what we will call connected. I mean, if that cannot be done, obviously, we call connected. There is a slightly other way to define it. I'll soon come to it. Okay. But this is a very general definition. Okay, now obviously let's come to the formal definition. Is the idea clear to everyone what we are trying to do? Yeah. For example, this will be whatever. If this is 2, this is 3, which is neither of them, and then 4. 2 comma 3 open, union 3 comma 4 open. This is topologically this part, yeah, can do analysis there by itself, can define differentiability continuity there without needing anything from here. And similarly, this can do on its own, right? They are self-sufficient in some sense. They are isolated from each other. Okay. So this is disconnected. Okay, and this is connected. This 2 comma 5 is connected. Well, one has to still prove, but for that I have to define it properly, what it means. But yeah, here is a definition. If the intuition is clear, then I'll come to the definition. Okay, so the definition is the following connected subset. So S being a subset, so let me say it very clearly. S being a subset of R is connected, okay, if, as a definition, if S is not the union of two subsets which are disjoint. Obviously, the first condition is that, I mean, this is not the entire condition, but which are disjoint. So we should not be able to write it as disjoint and, I mean, you can obviously write it as union of disjoint, but disjoint and A and B are both self-sufficient, are both open, okay, are both open. This, yeah, this is what I mean. You see, this definitely captures this, right? Here, if you break it up, I'm not saying that this is done, that we have proved it is connected, no, but you cannot break it up like this, right? Because this is not open, it's a closed subset, right? Because if you are at 3, you cannot move, you cannot make an interval which is inside it. Okay, so this is the thing. You should not be able to break it up into 2 pieces, and this notion of piece which are actually disjoint, topologically disjoint, is openness. That is the thing. Okay. Also, try to understand that if you do, I mean, you can make some very complicated thing this, and then you have this, right? I mean, even if so this is a part, and then you can take the pink part, right? Now you see, these two are this brown part and the pink part, right? Both are open, yeah. And also initially the way I was trying to motivate it, right, that if you have a point here, let's say this yellow point inside the pink part, then that is truly inside it, right? Which means that that yellow point is not the limit point. It's not the limit point. It's not the limit of any sequence which is in the brown part, right? Which means that there is a neighborhood around that yellow part which is inside this pink part, which is guaranteed and very crisply stated if you say that the pink part is an open set, or if you say that B is an open set. Otherwise, I could have made it a very complicated definition, right? Given any point in, so such that A and B are disjoint, and I could have said, given any point B in B, there is a neighborhood which does not intersect with A, which means it is inside B, and then blah. I could have done the same. I could make a complicated definition. But that is what we are trying to say by saying open. So is it clear, right? I'm trying to just make sure that you cannot break it up into 2 parts such that the limit points of one part are not in the second. But I'm just writing that in the language of openness. So you can already see open sets are quite useful. In fact, open sets are enough to describe they are enough to describe all of the non metric properties which depend on measurements. But that's a very hard thing to understand, to really understand usually if something is metric or not. So something might look like it depends on distances, but it may not, and something may not depend on distances, but using the concept of distances, you might find a simpler proof and explanation. So those are finer aspects which are so quite open-ended. So is this so clear so far? The definition, the motivation, and how you can view it in different ways. Okay, so it's clear. Okay, otherwise you can ask. Okay, so then since it's clear, now we can move to understanding what are all the open subsets on R. Okay, and then I'll just try to connect this a little bit with convexity, which we, for those who are there in the last class. Yeah, but either way, it will be easy. Convexity. Okay, we'll try to just connect it with that. That will become very interesting, especially when we do it in R2. I want to move to R2, and then I want to connect openness and connectedness, which is really what is needed in complex analysis. Okay. Just give me 1 second. I'll just take some water. Water is over. So yeah, so the next question is, what are all the open subsets of R? Sorry, what are all the connected? Classifying all the connected subsets, yeah? These are the kind of questions that are usually we ask when we introduce a concept. What are all the, we want to understand all of them. We want to be able to describe all of them using more primitive terms, using more primitive concepts. Okay, what are all the open subsets? Why am I saying open? What are all the connected? So that union, that will be a disconnected set, right? That's right. I mean, in the sense that will be disconnected. So yeah, so this is, so proving something is disconnected is not very difficult. You have to just produce a disconnection. Yeah. So this is just a point here, a small point. If you want to show that a subset S is not connected, right, then you have to just write it as a union of two things which are open and disjoint. But if you take this as an example, then this is obviously already given like that. So this is obviously disconnected. Yeah, disconnected. We are interested in what are all the connected components. That is what we're interested in. I mean, what are all the connected subsets? Of R. Obviously, it seems like intervals are connected. So, but again, we have to prove it. So yeah, let's think about this for a minute, and then let's please think, and then we will go into the proofs. So think of example, think of how you may prove something is connected. That's a little, right? How you may prove where it's connected. Because geometrically, it's an evident fact, maybe, but what is a yes. Yeah. So basically, I'm trying to say that we need to understand what are all the connected subsets of R? Okay, and more than that, I think a more specific question rather would be that how would you go about proving that something is connected? That's something that you can think about. Because you may obviously, because we are quite sure that intervals are connected. Are they all the connected subsets? And how do you prove their intervals are connected? So those are the questions that pop up. So maybe someone can. So just for R itself, it's a pretty good question then. Yeah. But the answer is obviously simple. That it seems fairly obvious that open, but then again, analysis is full of pathological examples, surprises. But it's a fairly straightforward situation. So it seems like intervals, right? It could be any interval, open, closed, half open. But yeah, so the claim is that intervals are all the open sets, right? Sorry, are all the connected sets. How do you prove? So let me then, since someone has said so far, so let me, yes. Okay. No, but you can't write. So an open subset is not an open interval. Yes. So when you say, okay, so let's, so the claim, make the claim is that A comma B is connected, then okay. Okay. No, but you cannot assume that it looks like C comma D. You don't know how that open subset will look like. So it's, see, by contradiction, it is not connected. So you assume it's not connected. Right. So if you assume that it is not connected, then this is a union of two. All you can say that it's a union of two disjoint open sets. Yeah. A and B are open and disjoint. Disjoint. But they're not open intervals necessarily. So open subsets are more than open intervals. Though connected open subsets are just open intervals, which is what will come out of this. Yes. Yeah. Okay. Yeah. No. So when you say a neighborhood inside this closed interval, then it will look like this. It can, it's this is allowed. So when you look at a neighborhood around A. So now A comma B is your world. R is not your world, right? A comma B is your world. So in that world, this is considered as an open interval. An open interval around A is like this. This is an open, this is actually considered as an open interval. This is open in A comma B. It is not open in R. In R, you cannot move. But in A comma B being the whole world, you can move because there is nothing to the left. In the sense that you don't go outside when you, that can be made precise by subspace topology and so on, but yeah. You should not go outside. That is the right way to say. So here is A comma B. And yeah. So we have a lot of open intervals. Maybe this forms A, and then we have B is here, and the disjoint. It seems it is not possible, right? It seems that it should not be possible, but how do we prove it is the question. So in some sense, a very simple fact that we're trying to prove. We're trying to prove that you cannot write A comma B as a union of two open intervals. So I'm trying to say that to disjoint is important here. Yeah? Even if it is open A comma B, just to remove any confusion, it will still cannot write. Okay, but we can keep it like this. And remember, both are non-empty. That is also obviously there. Okay, so please think about this. This is yeah, so you want to show that it cannot be written. How do you do it? Okay, think about this. Any ideas? I mean, basically you kind of feel that there has to be something missing, right? Something in between that will definitely, you will miss if you want to write A comma B as a union of two disjoint open sets. You know, disjoint and union of open intervals. A is a union of open intervals, B is a union of open intervals, right? So A is the green. A is the green, obviously. A is the green and B is the blue. Yeah, so the feeling is that something is there which you will miss. If you want to give them disjoint, right, you will have to miss something is very clear. How do you put a finger on that thing? And how do you mathematically bring it to existence? Yeah, how do you, what is there in analysis of math which guarantees the existence of such things or brings them to the surface or allows you to guarantees their existence formally? Because informally, there is nothing to prove. It's all clear. If anyone will believe, right? That you will miss something there in the middle. But what is that thing? How do you, what analysis guarantee? So that thing is the, just to give the hint, is the supremum of A. Okay. Supremum of A is basically the least number that is bigger than all elements in A, right? So supremum of A is X, then X is bigger than Y for all Y in A. So it's an upper bound, yeah, and X is the least such upper bound. Okay, we know that such things always exist. Yeah, it's a supremum. You can assume it just, okay, if you don't have to prove that it exists, obviously, but just assume that it exists. So X is bigger than Y for all Y, and X is the least such thing, okay, which again means that for any epsilon, probably all this is clear if you have seen the definition, otherwise you find this a little strange, but I'll complete the proof the next time. But think about it. For any epsilon, X minus epsilon is less than some Y in A, okay, meaning that X is the least upper bound. It's an upper bound, but it's the least, which means if you take anything less than X, then it's not an upper bound, so there will be a Y bigger than that in A. This is the number. This X is the problem. the supremum, you will see, will be the problem. Okay. Because just think about it, right? The supremum, so try to show from here that the supremum itself cannot be in A. Okay, the supremum cannot be in A. Try to prove that. That's because A is open. And it cannot be in B also. Again, try to prove that. Okay, think about how you can prove. That's because of the disjointness and because B is open. So please try to complete the proof. Try to do it on you, do it yourself. It's a standard exercise, so you will find it in some in a metric space book, or say Rudin or something like that. Untitled Chapter probably also it'll be there. But try to prove it from here because you have thought about it already. Okay, so do it. Try to complete. And obviously we will discuss this next time. Try to complete. Okay. So yeah, so this was the thing that intervals are connected. Okay. And also anything that is connected is an interval. That is another thing that can be proved. So that's again pretty simple. Okay. Anything, this is much simpler. Anything, I think, yeah. Anything connected in R, obviously, not in R2. In R2, it's much more complicated. The description, I don't think there is a description. Okay. Anything connected is an interval. Is an interval. Okay. I mean, once again, try to prove this. This is not difficult. Not difficult. You take something, if it is not an interval, so if you basically show if it's not an interval, then it is disconnected, right? And disconnected is easy to show. So something is not an interval, then it might be a very big set, whatever S is not an interval, so there will be a point in which is between 2 points of S, but that is not in S, and so you can, make a disconnection using that. Again, think about it. Yeah, and once again, let me just reiterate this point. In A, B, in A, B, in A, B, yeah, this is open. This is considered open in A, B. Okay, because there is nothing to the left of it. So in that sense, there is no, you don't go outside. Okay, so by the definition of openness, this is open. You can take it like that, or to be more formal, this is like, this is an intersection of some, A minus epsilon, this intersection with this world. Okay, so it is the intersection of some open set in the actual R. Okay, so that's why it is declared open. But for the time being, you can just keep it like this. Okay, that this is open, because if you do minus delta, then those numbers don't exist. So it's okay. It's vacuously true. But yeah, let's not go into too many metric spaces. So yeah, so are the ideas clear? Ideas of how you have to try to complete these things. You will have to complete this, try to work on this on your own first. Okay, because already we have given the idea. But yeah, okay. So we have seen that this is very, very clear. Yeah, let me not talk about convexity in R. It's not very interesting. Okay. Let us go to R2 straight away. Let us go to R2. And yeah, let's do that, and then we can understand. Yeah, now we are interested in connectivity. So I'm only doing those things about connectivity which are needed for us, in a sense that we're not trying to make it into an entire, section chapter on connectivity. Okay, that's not the point. That's not the goal. Okay, connectivity, we learn that later on. Yeah, connectivity in R2. So in R1, in R, it was a very simple thing, right? It was just what you would expect, and just the proofs are there, but it's what you have to prove is is a very simple statement, and proofs are also regular. Once you do these, more of them. Now we are interested in connectivity in R2. Okay, so you see, once again, before we get into this, we have to first understand what is an open subset in R2. What is the definition? Okay, definition of, because without having a proper definition, a crisp language which captures few words which captures, then discussion can be much more, okay, smoother. So the definition of open subset in R2. Yeah. So first of all, again, the intentions are very same. Okay, if you want a subset, okay, where if you make a not a neighborhood but a ball inside that, in the sense that you want to include those subsets in this definition, for which when you picking any point inside, you can put a little bit inside that. So if you make this, so what I'm trying to say is maybe this, then given any point inside, you can move inside it. Okay, so here the meaning of movement is you can make an open ball, just the usual ball, okay, just a circle. Yeah, there will be some ball which you can make which is completely inside. Now here we are talking about an open ball. It doesn't matter here. You can make a closed ball, half the radius of the open ball that you can make. But for the precise in the definition, we'll keep it like this. Okay. For any point inside, you can make an open ball inside it. That subset will be called open. Okay, that is called open. Again, you see, it's a very similar thing. Okay, to study local properties which depend on neighborhood of around a point like continuity and so on. This is what we desire of our subsets, right? And so it starts with open subsets, and then we go into defining connectivity using this concept of open subsets, and then we look at the special things, the special object of interest, which is open and connected. That is really what we're interested in, because we want to be able to do this local stuff, and at the same time we want to be able to move inside, in a way that we can draw curves inside, lines inside, polygons inside to do our complex analysis. Okay, that's why we are focusing on these kind of subsets, prove some properties about these kind of subsets in this isolated way, because the proofs will be much cleaner, and then we'll just simply reap the benefits later. So definition of open subset in R2. So again, just the ritual will just define it clearly so that it's very clear. S in R2, S in R2 is open if given any S in S, as if any S in S, there exists a ball. There is a ball of radius, some radius, I don't know what radius, centered at S. This is what this means, right? Just a ball which is radius S and centered S, radius RS centered at S. Okay, such that in S there exists this is completely inside S. Okay. Yeah, I mean, what I'm trying to say is that you can find a ball which is in R2 or on. Yeah, that is 1 second now. 1 second. Yes, yeah. So this ball has to be in R2. So I'm not saying you take the intersection of the ball with S. No, this ball has to be in R2, because we are asking the question if S is open in R2. Okay, if R2 is a bigger space, then is every point of S inside S, actually inside S, not set theoretically but geometrically. Okay, if you ask if S is open in S, then that's a different thing. That's not needed now. But S being open in S is a trivial thing. It's always yes, because there is nothing outside. So you obviously always inside. But yeah, just the definition of an open set. Okay. Once again, we can come to what is a connected set. So connected. And here we will give a more interesting definition in terms of paths, which is really which is equivalent in the case of opens, and that's the theorem we want to prove eventually, which is also there exercise in Stein Shakarchi. But yeah, let's so connected set in R2. Once again, we want to capture the same thing. We want to call a subset as connected if you cannot write it as a union of two, disjoint union of two things, which have nothing to do with each other, set theoretically or geometrically, meaning that they don't contain each other's limit points. Okay, so if anything is in A, and then its limit points, then that is in A. It's not the limit point of something in B. It doesn't have a close relationship with something in B. So something like that. Okay, so it's connected, and we just write it in terms of without limit points, just in terms of open sets. So connected set in R2. So once again, open set in R2 is just this. You can also say an open set in R2 is something which is a union of open balls. Anything that's a union of open balls is going to be open, and any open subset obviously is a union of open balls, because for every point you can make a ball, and those will eventually cover it, right? Obviously, yeah. So yeah, open balls, anything that is open, yeah, anything that's open is yeah, and yeah, okay. So connected set in R2. So S is formally S is connected if so S is connected if S cannot be written. S is never. So this can never be proved. So something is connected can never be proved directly in some sense, right? You have to show that, you have to assume that it is disconnected and get a contradiction usually. Otherwise it will be embedded in something like an inverse image of a connected set and under continuous function and so on. Okay? But yeah, by the definition, something is connected means that it cannot be written as a union of two things A and B, where A and B are open in S. Okay, open in S. So open in S means that A is something which is open in R2, and then you've taken its intersection with S, obviously, right? So that's what it means. Then it's open in S. So this is the definition. Okay, so if you want to show something is disconnected, let's write it as a union of two things which are. So once again, this union of two balls which are disjoint, two open balls which are disjoint is obviously disconnected, and so on, so on. Yeah, so let's connect session R2, which is this. Yeah, so what is it that I want to do next? Yeah, so now let me not rush too much, and let's look at convex sets. Okay, convex sets and convex set. Now the definition of convex set, you guys may have seen, but I'll still repeat: convex set in R2, or in general, but in R2. So convex functions we have seen. Convex sets are basically similar. So the typical example of convex sets comes from convex polygons. Yeah, convex polygons means something which all the angles are less than 180 degree. That's one definition which you have seen. Well, what does it mean more without using angles and such, right? What does it mean? What does it mean? It means that given any 2 points, that entire line segment is in the interior of the polygon. Just for a polygon. That's what it means for a polygon. Okay. Convex set similarly would mean that, okay, if X and Y is in R2, then the entire line segment containing X and Y is in R2. Line segment, obviously, only. Then lambda X plus 1 minus lambda Y. So this is obviously it's a vector, or a point in R2, or rather this family of points in R2 is in. So I'm saying that is in C. So C is the convex set. Looking at it is in C for all lambda in 0, 1. Right? So this is what it means to say that the entire line segment is in it. So this is just another definition. Okay. Now here's what we want to show. Okay. So first of all, try to understand that. Try to understand that intervals are convex, right? That's absolutely clear. In fact, intervals are convex, right? Try to again for intervals in R, right? Try to maybe note it down and try to show. This is a good exercise to do again. Okay, is that find, just I'll say find all convex. So you understand what the definition of convex is in R. Just these are in R. Okay, find all convex subsets of R. Please note it down and try this if you can't immediately see. If you can see, then that's very, very good. But just try to write it also. Okay, find all just the way we have described all connected subsets. Try to describe all convex subsets. Try to do this. Spend time and try it even if you can't do it immediately. Okay, find all convex subsets of R. But we will move to thing. Convex subsets in R2. Okay, so obviously this is the thing. Now what we want to show, see, intuitively this should be clear, right? That if you have a convex subset, so forget about this, is clear. But that's the interior of that is convex. This is not a convex subset. Yeah, it's not convex, right? Because if you take this and this, then it's outside. If I mean this is a thing that's inside, right? So that's not convex, okay? But if I do draw a convex subset, then you can see that it seems like it should be connected. You see, you can see that, and that's a very those are important later on, significant topologically also later on, where we want to do these things without the notion of distances and intervals based on distances and based on balls, but not measurable balls, but the balls by declaration, kind of. Okay, but in any case, this is kind of a convex subset. Okay, what I mean is the interior as well. I want to include that also. Okay, so what I'm doing is I'm saying that if you take any 2 points, the entire line segment is going to be in it. Yeah, and for any 2 points, obviously. So it certainly seems like this is a connected set. How do we show? So this is certainly again something which is geometrically evident, but we want to show. This is the first step to discovering a very interesting type of connectivity, which is very useful and also it's equivalent in our case of our interest. Okay. Show that convex subsets are connected. I mean, convex subsets in this case, convex subsets are connected. Let's think about this. Again, you see that this looks very simple, but it might be because here you see we do not have that. We do not have the supremum in a direct way. We do not have order. So in R, we exploited the order to prove those things. But even though those proofs can be done without the notion of order, but we use that extra thing that is there in R. Here it is slightly more crazy because you don't have an order or a useful order. We have orders, but they are not useful. Let's think about this. Any ideas how we can? So I'm not saying anything about it being open or closed. That is not relevant. But for any 2 points inside, so usually open and closed don't affect connectivity too much. It's loose sense. We'll make it precise. But for the time being. So I'll just write a first line, assume that it is not, this is usually the route we take. Assume that if you're proving it from first principles. So if it is not connected, then what is it that it will look like? It will be then a union, disjoint union of two. Obviously, later on we'll prove a theorem from that, it will easily follow, but to appreciate it, we'll have to try to see this. So you see, then you will have, just for simplicity, there will be a big open set, yeah, which will contain one part of it. And then there will be another open set that will contain another part of it. And they will be disjoint. Yeah. Obviously, this is not done because this is missing, but roughly speaking. Okay. And what does it contradict? What is it about C that does not allow this? Maybe I should make my picture different. Once again, it looks very clear. See, convexity basically means that all the things that you can see inside are actually there. Yeah, it means that all of this is actually there. Yeah, these are actually there. There are no holes. Convexity is actually much more than connectivity. Yeah, is that there are no holes. That's what this condition is saying. Okay. So how can we use it? So you see, the contradiction comes from something like this. Again, this is the idea. So let's say something like this, and then it is very clear that there is not possible, right? But what is it about this that is making it not possible? It's this. If you make two open sets like this, two yellow blobs, right? Then the point is that, look, you can take one point which is in one of them and the other point which is in the other of them, right? Now the line, there has to be a line that passes through them, right? Now you can think. Yeah. if this is the A and this is the B, and this is the X and Y, so we have picked not just any arbitrary X and Y, right? We have picked the X that X is in one of them and Y is in the other of them, right? Then you can see, right? The line segment that you join has to at some point cross from one open set to another open set, right? Yeah, the line has to cross from one open set to another open set, and that lines don't allow that because lines are connected, right? To make it precise, to make it very precise, or just to make it slightly more precise, okay, you can try to do it yourself if you want, but otherwise you can listen. To make it precise, here is what we do. You just simply, you look at this line, you can take closed or open, doesn't matter. This, you take its intersection with A, right? A is that big thing. And then you look at X and Y and you take its intersection with B, yeah? A is open, right? A is an open subset, right? So its intersection with X comma Y, this is open. Where? It's obviously not open in R2, right? But as far as X comma Y is concerned, it's open. Open in X comma Y. Yeah, it is basically just like something like this maybe, yeah, but it is open. I mean, you can try to prove that more rigorously if you want. Pick a point, it's in S comma Y, it's in A, so you can make a neighborhood which is in A, which is, yeah, so you can do it. And similarly, this is also open in X comma Y. And there you go. And it's obviously disjoint because A and B are disjoint. Roughly speaking, this is the proof. This is more precise, I think precise enough. But what we'll try to do the next day is we will frame this in terms of continuous functions. Like how continuous functions capture this and generalize this. This is like a linear function from 0, 1 to this set, which is at 0, it is y, and at 1, it is x, or vice versa. It's a linear function. And we will say more about that. Okay. So then we will come to, so it's not just continuous, but it's not just connected, right? It is more like from any place to any place, there is a path. So we'll make this notion of path precise next time. Then we'll define a new kind of connectedness. Then we'll push a stronger, look stronger, and it is stronger in general. But then we will show the main theorem that we want to prove is to show that a stronger notion is the same as this. And then you want to look at connected components because that's another thing which is needed. Okay, so those two are the actual exercises in Shakarji, which you can still try already if you want to. Otherwise, you can just wait. Okay, and we will do it next time. Okay, yeah, I'll certainly do it next time. Whether, yeah. So that's it from my side for today. Are there any questions? Okay, so okay, yes, sure. So that question was, I have still not thought about it. So the question is that if you look at the list of primes, so this is the usual list of primes, which is 2, 3, 5, 7, and so on. Then we want to show that there are infinitely many primes. I just say primes Pn such that the kth prime to the left versus the kth prime to the right. The kth prime to the right of n is farther from Pn. Okay. So this for all k less than n. Yeah. Again, I had said what I understood from it, but I don't yet know how to do it. Oh, okay. All right. Okay, so I think that's okay then. Maishwari, do you have any questions? Because you joined for the first time. Okay, so then, okay, good then. Okay, then that's it for today. Thank you.